Right. Hello. Hyvää iltaa. I've heard there's a lot of Finnish people in the audience. There's my slides. Everything's working. Good. Okay. Nice to be speaking at Euroclosure again. I can't see any of you. I got these bright lights in my eyes, but I'll assume that you're all out there. I was going to start off by saying it's about time somebody did some actual live coding in Emacs, but Alex ended very strongly in the last talk, so we got that covered, so I might as well just skip my talk and we can all go to the party. Oh, I can actually try and do something up here. So what I'm going to do, there's one thing that hasn't been done much today, and that's running things backwards. I feel this is rather important at a Closure conference. We got a tradition of logic programming in Closure. We've had Dan Friedman and Will Bird come talk about miniKanren quite a bit. It's always equally mind-blowing. We got core logic, which is actually a thing in Closure. Dan and his new student, Jason Heeman, recently published a paper called microKanren, where essentially they reduce the whole idea of microKanren into some very basic small concepts and write a very short and succinct scheme program that essentially does what miniKanren does, except smaller and a lot more easy to understand. And that's going to be my aim today, to show you this magic and how it actually works. So relational programming is essentially a program that doesn't just take inputs and produce outputs, but it takes inputs and outputs, and then it sort of figures out which part of it is missing. This is a very simple relational program, which we're going to try and be able to run at the end of the talk. This is an even simpler one. This is really boring. What this means, the fresh declares a variable. So we're saying, let's introduce a variable q. And the append function is a concatenation. It takes two lists and produces a list which is the concatenation of the two previous lists. So the difference from normal Closure is that instead of taking those two input parameters, we also put the output parameter in. And in this case, we've made it the variable q. So the job of this program is to infer what is the value of q. And can you do that for me, please? What's going to be the value of q? List of 1, 2, 3, 4, 5. This is, there can actually be more answers to most relational programs. So what you're seeing here is a list of 1, 2, 3, 4, 5, which is the only answer. But there could have been more, which means that the list would have included more answers. And this one is slightly more interesting. We are introducing essentially q as well as a and b. And the reason we introduce q at all here is because we usually only get the value of the first variable we declare out as the answer. So we're simply saying that q contains a and b, so that we get the value of both a and b inside q with the double equals function. And then we call the append again, except this time we only produce the answer. And a and b are the inputs, and the job of the program now is to figure out what a and b are. And what are they? In this case, actually, we can have multiple answers. We can have empty list and 1, 2, 3, 4, 5, 1, and 2, 3, 4, 5, and so on until 1, 2, 3, 4, 5 on the empty list. 6 different possibilities. And this is magic. This is like, wow, how did this happen? I have no idea what I'm doing. What I'm going to do today is show you how it's done, the magic, sort of peek behind the curtain and show you how the real work gets done. So there are 3 core concepts of microKanren. First, there's the concept of state. State defines a set of relations and a variable counter. Essentially, we have a map which contains bindings from logic variables to values, or possibly other logic variables. And we have a variable counter. Essentially, when I want to introduce a new logic variable, what I do is just increment the counter and take the value of it, and thus I have the name of the next available variable. In this case, we've defined two variables, hence the counter is now 2. The variable set of 0, I've used the convention that, as I'm not able to use sets in microKanren anyway, I'm just borrowing sets to be like the data type for logic variables. And the set only contains one thing, the name, which is 0, and it's bound to the number 1, and the variable 1 is bound to the number 2 in this case. And we have streams, or essentially later lists of states. Essentially, when you run a relational program, what comes out is a stream of states which satisfy the program. And they look simply like a list of these states that I just described. There can be several, there can be none, in which case the program has no answer. We have goals, and the goals are sort of the program itself. A goal is applied to a state and returns a stream of satisfying states, possible given that starting state. And a goal is essentially a function which takes a state in. Notice that I'm using some destructuring there, which is a common pattern in microKanren, at least in my Clojure implementation of it, where I take out the state bindings and the counter. And in this case, what I do is essentially declare a new variable, but I don't do anything with it. So essentially, I'm just wasting a variable. I increment the counter and return the same state without binding the new variable to anything, which is just the stupidest example I could think of. So we've got states, we've got streams, and we've got goals. States are program states. Streams are answers, which contain states, and goals are sort of the program itself. They're functions, which take us from one state to 0 or more new possible states. There's a description in the paper, essentially what microKanren is. It says a given collection of goals may be satisfied by 0 or more states. The result of a microKanren program is a stream of satisfying states. And so I hope that makes sense to you now. Fundamental operations. They define 4 of them, like the 4 most basic things you can do in a logic program. Define a variable, define a relation, which says that something is equal to something else. Disjunction, which means you have one goal or another goal, and if one of them is true, then you have an answer. Conjunction is and, essentially. If you have 2 goals, both of them must be satisfied to produce an answer. And that's enough talk. Let's get to the programming. Emacs. Should I increase the font size? A little bit, I think. There. If I could see my Emacs. There we go. OK. So the problem with implementing microKanren in Clojure is that microKanren relies heavily on const cells, and Clojure has none. And despite that, it calls itself a list. But still, I'm going to try to be sorry about that, but I had to implement this yesterday to make it work. Essentially, I got an implementation of a const cell-based list. I've given first and rest, as you call them in Clojure, their proper names, car and kada, just for the occasion to make it more readable. And essentially, I've implemented cons. I've made this a def type and a def protocol. And we have cons, car, and kada. We have a list function, which lets you construct a cons list very quickly. And that's it. So first of all, let's see how much time have I wasted. Didn't start the timer. Great. 10 minutes. OK, we've got half an hour. This should be good. First of all, we need functions. Well, functions to define variables. You'll notice, by the way, that I've excluded a lot of things up here that I'm going to redefine. But I wanted to call this var, but var isn't actually redefinable. So I'm calling it lvar for logic variable. And that simply takes a number c and returns my convention of using the set as a logic variable. So a set that contains only the number c. And I want to be able to test if something is a variable. And that's very simple. Just test if it's a set. So I want an empty state, which is going to be an empty map and the number 0. This is the starting state of all microKanren programs. Let's see, I got a REPL up here. Let me just test if it works. Yeah, it does. IEEE 754, ladies and gentlemen. Let's compile that. Well, unable to restore symbol properly. Oh yeah. Single pass compilers. I mean, I could just recompile it and it would probably work, but I want to make a point of this. What was it, just properlist? Properlist. Okay, now it compiles. Well, okay, so if I go elvar 0, I get variable 0 down there. And elvar question mark, elvar 0 returns true, brilliant. Elvar question mark, lol, is false. That looks good. Okay. So next, I want a function walk. And the function walk takes an arbitrary value and a mapping from inside the state, which we'll just call S for state. And the task of walk is to look through the state mapping and resolve the value that you pass in. If it's just a value, then it should be returned as it is. If it's a variable, we need to look through the table and figure out what it's bound to. And you have to keep doing that, because it might be bound to another variable, which eventually is bound to a value. So we go if u is a variable and contains, if S has a mapping for it, then we call walk again. We do some recursion with the value that is bound to, and S again, which means that if it's bound to a variable again, then we keep calling it until we get a value out. And if it is just a value, just return the value. So walk 1337, empty map should get us 3037, walk logic variable 0 with an empty map should be logic variable 0 because there's no binding for it. If we add a binding, it should resolve to the value of the binding. If we bind, if we bind 1 to 0, that should resolve to 0 and then to 1337. Oops. Unmatched delimiter. This is embarrassing. Where's that? Oh, yeah. Sorry. Ah, there we go. That was not a parenthesis error. That was a curly brace error, so I'm blaming C. OK. Looks good so far. Next, we add just some bindings here. We want the functions for making a stream of no answers. We call that M0, and that's just nil. That's the empty list. And, sorry, that would be def. And we want a function unit, which just takes one state and returns that state as inside a list. So M0 and unit, don't panic. I know this sounds suspiciously like concepts from Haskell. Don't ask what the M is for. But it's fine. It's just, they were used in the paper. I'm just reusing them. It just means empty stream of answers and stream of answers with one answer. And next, unify. This is where it gets interesting. We want a function that says, take these two values and unify them, which means that we declare them to be equal, and then note that in the state. So we can say 1 equals 1, and that doesn't need noting in the state, so we would just return the state unchanged. We can say 1 equals 2, which is obviously incorrect, presumably, and that would return nothing, because that is obviously not true. We could bind logic variable something to a value, and that will be noted. So let's try and implement that. First, we need to resolve U and V. Just by walking them. And then we have a very big cont. First, if U is a variable and V is a variable, and they're the same variable, then just return state unchanged. That doesn't need noting. But if U is a variable and the previous isn't true, then we note that U and V are equal. Essentially, we associate U with U as the key and V as the value in S. So same goes for V. SVU. So that allows us to say variables are equal to values. And we need to be able to do this inside lists. So this one's a bit interesting. If U is a list and V is a list, then get a new S where we unify the first element of the list, the car, and the first element of the other list. And if that hasn't failed, and does, then we unify the rest of the list. Cut it V of S. There we go. And as our else clause, we just check if U and V are equal. At this point, they should be just values. Then we return S. And if the equals test fails, that means we get a false out, which means no answer. So let's test if that works. So let's try and unify 1337 and 1337 with the empty list as the empty map as an input. That gives us the empty map back. That means there is an answer. We didn't need to note anything about it. It works. 1338, we get false. That means 1337 and 1338 are obviously not the same. What if we bind it to 0? We get a binding out. It now says that 0 is 1337, which is good. Now let's make it interesting. This 1, 2, 3. This 1, 2, 3. That's good. 1, 2, 4. Sorry. That's false. That's correct. 1, 2, 3, 4. Just to test if it checks the lists are the same length. Yes. And now we can also go 1 to logic variable 0. And that actually picks the 3. Note that the 3 is in the third position in the first list, and the 0, the logic variable 0, is in the third position of the second list. And so we figure out that the logic variable must have the value 3 for these lists to be equal. So we're sort of almost doing proper logic programming already. But let's get the operators in. Equals U and V. So this takes two values and makes a goal that says they're equal. And a goal, as I noted, is a function which takes a state, which contains S and C. And we say S is the unification of UVS. Essentially just run unify on the inputs. And if that didn't fail on us, then we return unit S and C with a new value of S. That means one answer with a new binding. And if that fails, we return M0, no answer. So now I can go on S1. And if we run that with empty state, essentially call the function that is returned, that you can see just there with a funny name. With empty state as an input, it should run the program for us. And note that we have no bindings, no variables, but there is an answer. 1 is indeed 1. Note the difference. We get an empty list back if we try and pretend that 1 is 2. Okay, and the same applies that I showed you with the unify for the logic variables and whatnot. But we need to be able to bind the logic variables as well. So I'm going to introduce a function called callFresh, which takes a function and returns a goal, which declares a variable and passes it on to the function. And we call the function with a new variable that we make, and we increase c, alvar c, sorry. So we take the current value of c, we make a variable out of it, we pass it on to the function that we pass as an argument, and we return, and we run it essentially. This returns a goal, so we run it, returning this state. Sorry, passing this state in. And this statement simply notes that we have used the variable c, so the next one will be c plus 1. So now we can do something like callFresh with a function that takes a value q, which is going to be the new logic variable. We can note that q is equal to 5. And if we run that with the empty state, we get a state out saying that, yeah, logic variable 0, our q is 5. That's good. And note that it has a 1 on the end, which means we've incremented the counter properly. Okay. Now, in order to implement or an and, which is sort of required to do programs that are slightly more fancy than just saying one thing is equal to the other, we will need some helper functions. And plus, stream 1, stream 2. And plus is simply concatenation. And if stream 1 is a list, then we return cons of car of stream 1, and plus coda stream 1 and stream 2. This is just a recursive concatenation, really. There's nothing fancy to it. Essentially, if one is a list, keep recursing until we've expended one. And if one is not a list, that means one is the empty list. Then we just return 2. So that means if we test this, we have list 1, 2, list 3, 4. Hopefully we get, yeah, list 1, 2, 3, 4. Good. And bind. Bind is the M word bind, which simply, if the stream is a list, then M plus run the goal. Well, you pass the stream and a goal in, and you apply the goal to all the elements of the stream, essentially. Sort of like map. So we apply goal to the start of the list, and then we recurse on the end of the list with G. And if the stream is empty, then return the empty list. Okay. Sorry? Oh, yes, correct, thank you. That's it. Okay. So that makes it easy for us to implement the disjunction and the conjunction, just to make sure we don't get too comfortable. I'm not going to call them or and. I'm going to call them disj and conj. Goal 1 and goal 2 returns a function that takes a state, and M plus is G1 of that state and G2 of that state. Good. Conj is basically almost exactly the same, except we bind with G2. Okay. So now we can get interesting. Let me just see how much time I got left before I get too interesting. How much time do I have left? 15 minutes? I think so. Okay, good. So I can go distger. Well, I need to call fresh first. I need a variable, q. And then I can say distger, q is 1, and q is 2. And that gets me a goal function, and I call that with empty state. And I get 2 answers, q is 1 and q is 2, so that looks good. Now if I change the disjunction to a conjunction, I get no answer because q cannot be both 1 and 2. But I can say that q is 1 or q is 1. That satisfies the and, because q is indeed 1. Okay, so that seems to work. Just let me add a function, because I'm sick of calling it an empty state all the time. Let's make one called call goal of g, which just does that for us, g of empty state. So I just go call goal and get rid of the empty state. And that's the same thing. Okay. So let's get fancy. Let's create a goal of 5s, which is the disjunction of x equals 5, and a new goal which says x equals 5 again. What we got here is an infinite stream of answers saying x is 5. And at this point, we realize we might have a problem, because if there's an infinity of answers, what happens if I try to run this? Actually, I need to call fresh this, call fresh 5s. Luckily, we don't go into an infinite loop, because closure still does not have tail corner elimination, so we get a Stack Overflow instead. That's not good. We want to be able to handle this. We did mention that the stream is supposed to be lazy. So let's add laziness. And that's really simple, actually. We just need to modify ampersand bind to be able to, essentially what I'm going to do, instead of just returning this one immediately, I'm going to wrap it in a closure. And then m+ needs to check whether we are passing in a closure, which is just going to be a function. If so, then we return a new function where we essentially make a new closure where we unwrap the first closure. And likewise with... You need to stop me when I do stupid things like this. It's supposed to be inside the cond, obviously. There we go. Okay. This one should read bind instead. And this should read nothing and g. Okay. But that's probably not going to work as is. Well, yeah, I saw it. Thank you. Okay. So what happens now? We get a list of the first answer and a function. We need to actually make something to unwrap that. And let's make a function pull, which takes a stream, and if that isn't a stream but a function, then we pull again, unwrapping it, and if it isn't a function, we just return it as is. And then we need a function take, which lets us specify a number of answers that we want to take out of the stream. This is almost exactly like the take function in normal closure. If we want 0 answers, then we get the empty list. Otherwise, we pull and we recurse. What? Nil cons car take recurse here, and the coda, and that's it. Okay. We could also make a take all here, but I'm not going to bother because I'm not going to need it. So take 10. I guess there's 10 answers of 5s. So that works. We've made it lazy now, and it doesn't go on forever until you Stack Overflow. But there's another thing that could go wrong. Suppose we have 6s as well. Essentially, sorry, Emacs failure, multiple cursors. So return 6s. And then we make our 5s and 6s goal. Call fresh, function x, distra, 5s of x and 6s of x. And now take 10 of call goal 5s and 6s, get a list of 5s. That's annoying. We have an infinite list of 5s and an infinite list of 6s. And as it happens, we do depth-first search, which is what Prolog does, but Prolog is old and uncool. And what miniKanren is supposed to do is an interleave search. Essentially, we should get an answer with 5s, an answer with 6s, then 5s and 6s towards infinity. How do we do that? Actually, this one's really simple. Really simple. We just swap the order in the AND+. That's it. And now we got 5, 6, 5, 6, and so on. To infinity, we can take 100. That's a lot of 5s and 6s. We can take 1 million. And I got a bit ambitious there because we're still on the stack, but you get the idea. There's a lot of them. Cool. Huh? Yeah, I know, right? But this is a closure conference. I thought I'd do it in the traditional way. So, okay. But that's actually our miniKanren implemented for us. I'm just going to get the appender, I'm just going to take the opportunity to copy a lot of macros and things, because I don't want to type these out, and especially since I have 8 minutes left. So I made this for you. Essentially, it adds things like the run macro, which instead of me typing take 1 million call goal, I can just go run 5s and 6s. Run 10 5s and 6s. And it's got the fresh macro, which instead of doing the call fresh with a function, I just say fresh queue, as you saw at the start. And we got the cond, but I think I'm just going to stick with the content distra to make this clear. So now I'm going to make the append. Yes, I think I have time to type it out. For maximum excitement, just check that this compiles. It does not take, oh yeah, I didn't implement take all. But that's only required by run star, so I'm going to remove run star. And now it compiles. Yay. Okay, so the append. This one is a mind bender. It takes a lot of getting used to how to write programs in miniKanren. And fortunately, somebody did this before me, so I just sort of copied it and tried to figure out how it works. Essentially, append takes 3 variables: the left hand and the right hand and the output. And of course, the output should be the concatenation of the left and the right hand. So let's do that with old-fashioned distra and conja. We start off with a disjunction or and a conjunction which says L is nil and R is out. So what this says is if the left hand is an empty list, then obviously the output must be just the right hand, because an empty list concatenated to something is just that something. So this is our terminating clause. This is sort of like writing a recursive program, like in Haskell or old school Lisp, or a Lisp with tail recursion. And then we need variables, small variables, AD and res. A and D, of course, referring to the address and decrement registers from current coder. A means the head, and D means the tail. We use A and D for clarity. Head and tail are like fancy Haskell words. And now we say if cons A onto D is L. Well, not if, we say that. L equals cons A and D. That means that what A and D are going to sort of contain here is A is going to be the head of L, and D is going to be the tail of L. And equals cons A res out. Now we get fancy. Now we say that out, well, A is also going to be the head of out, and res is going to be the tail of out, which means that res has to start with D at least. We don't specify that relation, but it's implied through logic. Okay, that's it, and we recurse. I should note that the fresh macro, it wraps everything in a conj. So all my statements inside the fresh have to be true. And also, it wraps them in that lazy closure thing. So I don't have to worry that I just go into an infinite loop and blow the stack when I just call appendo again directly here when I recurse. This is going to be like closure appendo. And DRS. So we essentially create a goal which instead of saying LRS, we say DRS, and D is L without its head. And so that's going to go through all the elements of the left-hand list until it reaches the first statement there, which says the left-hand list is empty. And at that point, we should have our answer. And we sort of go out of the recursion and figure out what the answer is. So now let us do the actual program. Run 10. Fresh QAB. Actually, let's do the stupid one first. Let's just see if it works at all. I'm nervous about this, you see. Appendo. List 1, 2. List 3, 4. Q. And that says Q must be, note incidentally that my run macro unwraps my states and just returns the contents of the first logic variable that I declare, which is Q. So what's inside this list now is the contents of Q and nothing else. And that is 1, 2, 3, 4, so it looks like it works, at least for the simple case, which any programming language can do, even closure. Is it concat? Yeah, look, closure can do the same thing. What closure cannot do is run this backwards, which we are now about to do. What closure obviously can do, because I'm writing this in closure, but you know what I mean. Appendo. That was 1, 2, 3, 4, 5. AB. And I also need to say that Q is A and B. List of A and B. Okay, big moment. Before you can go party and not think about this. Right? My Lisp sentence is tingling. Actually, my Emacs is highlighting the wrong parenthesis, which means they're not balanced, if this is right. And we get the answer. Empty list, 1, 2, 3, 4, 5. 1 and 2, 3, 4, 5. 1, 2 and 3, 4, 5. 1, 2, 3 and 4, 5. 1, 2, 3, 4 and 5. And 1, 2, 3, 4, 5. An empty list. That looks correct. So, yay. So that was essentially like several decades of research on the part of Dan Friedman and company in half an hour. No big deal. It's cool though, isn't it? Anyway, that was it. Then go have fun. Thank you very much.